Hi, in this video we are going to learn about first order logic, and I assume that you are already familiar with propositional logic. So before getting into the details of first order logic, let's try to see what are the advantages and disadvantages of propositional logic and how does first order logic helps in addressing some of these disadvantages. So before looking at the cons, let's look at the pros. So propositional logic is known to be declarative. And what is declarative? So a proposition is a declarative sentence to which we can assign a truth value, and this truth value can be either true or false. Okay. So this is a pro of propositional logic because it helps us in simplifying our notions of what is right and what is wrong, and thereby helps us in arriving at clear cut inferences. The second one is that propositional logic also allows partial, disjunctive, and negated information. Partial information, like we have seen in some of the examples where we do not have full information about a game, we can use propositional logic to even represent that kind of partial information. Propositional logic is also compositional, meaning that you can take smaller components, and combine them in various ways recursively to make a composite statement which can be a lot more complex than those simple, parts of the whole. And fourthly, propositional logic is context independent, and this is very different from natural language, which, as we know, has a lot of context embedded into it. Right now when I'm talking to you using English language, the reason you are able to understand what I'm saying is because you already have the context which I am using to say whatever I am saying. But this is a problem for computers because computers do not have the knowledge of the world like we do. So because of that, for any system of representing knowledge, for that to work for computers, it has to be context independent, so that a computer can make sense of what is being asked of it to be done without having any understanding or knowledge of the world around. And that is where propositional logic also helps, because it is completely context independent. So these are the four major advantages of propositional logic, why it is so powerful. But there is one major disadvantage which limits its usage for computation, which is that propositional logic has very limited expressive power. So there are some sentences which could be written in propositional logic, for example, but that would take a lot of space and lot of time to express something that is very simply represented in English language. For example, for the, if you remember the Wampus World game that you had, where we know that pits cause breeze in adjacent squares. If we had to represent this using propositional logic, we would have to write a separate sentence or a formula for each pit in the game, and that would take a lot of time and space. And this is something that we simplify using what is called first order logic. So first order logic is in a way not very different from propositional logic. They are related to each other very deeply, and the primary difference is that what requires 20 or maybe 100 sentences in propositional logic can be represented in a very simple and compact form if we use first order logic. So it is just a so to say a minor change of representation which gives first order logic immense power over propositional logic. So first order logic in this sense is an extension of propositional logic, and it is not something that is totally different from it. And first order logic can express many more statements from natural language as compared to propositional logic, but of course not all. There are still statements in natural language which cannot be expressed using first order logic, and one of the reasons is because natural language is very heavily context dependent. You cannot take away the context from everything that is said in natural language, but it is definitely expressive enough to serve the purpose of computation, which is what we are really interested in. And first order logic is also called predicate logic. So predicate is basically the part of the sentence which has the verb, which tells us what is it that the subject is or what is it that the subject does. For example, if you have x is an integer, then x is your subject and is an integer will be your predicate, which basically tells what is it that x is supposed to do. So propositional logic is purely based on factual statements. So for example, x is an integer. This is a factual statement. So this whole thing will be taken as a single sentence in propositional logic, and you can assign to it the value of true or false. But in first order logic, we don't just take, sentences, but we take different concepts and different objects and we try to find relationships between them. So in first order logic, instead of representing this thing as just one sentence, what you will say is that x is an object, integer is another object which could also be a function, and you will find a relationship between x and what is called an integer. And the relationship may hold true or may not hold true, which is equivalent to the propositional statement being true or false. Okay, we will see some examples which will make it quite clear. So in first order logic, some of the objects could be some symbol a, symbol b, or some people, some numbers, colors, words, and lots of these various things can be different kinds of objects that are used in first order logic. Then you have relations between these objects. So these relations could be unary, it can be binary, it can be tertiary, or any n-ary. So what does unary mean? Unary means that it is the relation of the object with itself. It is basically some property of the object, and you do not have to invoke another object to define a unary relation. So I can ask whether my object is red or not. I can ask whether my object is round or not, and so on. If we take example of binary relation, I can take two objects and I can ask, is one object a sister of another object? So that will become a binary relation because I have now incorporated, or I am using two different objects to define my relation. After relation, we have another concept which is called a function. So a function is also like a relation, but the main difference is that a function cannot be one to many. Okay, so if you give a particular input to a function, you are supposed to get a specific output. It can be many to one, but it can never be one to many. Okay, so that is the difference between a relation and a function. So a function is a special type of relation. Okay, so this is primarily what first order logic is made up of. It has objects, it has relations between those objects, and it also has functions between those objects. Now in propositional logic, we had certain atomic sentences, and we had various kinds of connectives and operators. In first order logic, all those operators and everything is going to be used, but in addition, we have some extra things that gives first order logic a greater power over propositional logic. So one of the basic things that first order logic has is what is called a quantifier. And one quantifier is this universal quantifier, which is denoted by this symbol, which is called for all. The other quantifier is this symbol, which is the existential quantifier, and its meaning is there exists. Okay, so we will again see how exactly these are used shortly, but just remember for now that this is the universal quantifier and this is the existential quantifier. Then next we have some constants, and these are basically our objects. It can be some symbol A, it can be some symbol x1, or it can be the name of a person John, and so on. Then you also have variables, which we had in propositional logic also. But more importantly, now you have predicate, which is basically the verb that describes the subject or tells us what the subject is or what is it doing. And then you have functions, which are described over the objects. Now, in terms of the various kinds of operators and connectives, all of that what we used in propositional logic is still there, but in addition we also have a new operator, which is equality, and this signifies that the two terms are referring to the same object. So when you, let's say, have x equal to y in first order logic, what that would mean is that the object x is exactly equal to object y, and that is how we define the equality between two different objects. So this is basically the instruments that we have in first order logic, using which we are going to do all the interesting computations and inferences to arrive at suitable conclusions. So let's look at these quantifiers and understand them in slightly more detail. So let's say we have a sentence in English called all birds can fly, and now our objective is to describe this using first order logic. So if we had to do it using propositional logic, what we will have to do is that we will have to write a separate sentence for each bird that can fly, and we have to say parrot can fly, peacock can fly, pigeon can fly, sparrow can fly, and so on. So that will require us to write thousands and millions of sentences depending on how many birds are there on this planet. But in first order logic, we do not have to write so many sentences, and actually just a single sentence is sufficient to capture what this English statement is trying to say. So the first thing we do is that we first identify what is the predicate, and that predicate over here is fly. Okay, so we define two functions, one is bird and one is fly. So bird of x will be true if x is an object which is a bird. Fly of x will be true if x is an object that can fly. Okay, and what is it that my English sentence is doing? That for all x, when bird of x is true, which means that x is a bird, then I know that fly of x is also true. Okay, and that is what this quantifier means. This is a universal quantifier which is for all. So it means for all x, if you take any x, then this sentence is true, which means that if x is a bird, which means bird of x, if that is true, then fly of x also has to be true. Okay, so as we see, in a very simple way, we have been able to represent the English sentence using a single sentence in first order logic, unlike propositional logic where we would have to write a separate sentence for every single bird that exists on this planet. Let's take another sentence. Some boys play cricket. So here the predicate is play, and so we can have two functions. One is boy of x, another one is play, which takes two arguments. So this boy of x is a unary function, and play x comma cricket is a binary function because it is taking two inputs. So play x comma cricket would be true if x plays cricket. Now notice we could have used a different function called cricket bracket x, but the thing is that in that case we would need a different function for each game that we are interested in. But the advantage of writing it this way is that we can just keep changing cricket to basketball, football, baseball, whatever, and the same function play can capture the idea that whether this x plays that particular game or not. So now what does this say? Some boys play cricket. This is different from the previous one where we had all birds can fly. Okay, so here in some boys play cricket, we cannot use the quantifier which is the universal quantifier. So now we have to use the existential quantifier, which says that there is at least one x for which boy of x is true, and that implies that play of x comma cricket must be true. Okay, so this sentence is true at least for 1x. So here there is some ambiguity because it says some boys play cricket, which means that usually larger than 1. So that we cannot exactly capture using first order logic, and that is some limitation that we see over here. Okay, so now let's take another sentence which is slightly more complicated. Not all students like both mathematics and science. So here the predicate that we have is like. So we have two functions and we are using the same function like twice. So we have one unary function called student of x, which outputs true if x is a student. Like x comma mathematics will be true if x is an object that likes mathematics. Like x comma science will be true if x is an object that likes science. Okay, so what do we now know? Not all students like both mathematics and science, which means that not everyone likes both mathematics and science. So there are students who like mathematics but do not like science, and there may be students who like science but they do not like mathematics. Okay, so the way we represent it is like this. So we have a logical and operator over here. So it says like x comma mathematics and like x comma science, and here we have put a not. Okay, so if this not was not there, it would mean that for all x, if x is a student, then he or she will like mathematics and like science. But the moment we have put a not in front of for all, what that means is that this particular statement is not true for all values of x. Now whether it is true for no value of x or for some value of x, that is again an ambiguity which we do not have any way of clearly specifying. Okay, so that we have left out as it is. So what this means is that for all x this is not necessarily true. Okay, so not for all x this thing will hold. Okay, so now let's look at slightly more complicated examples to get you a better feel for where this is leading to. So let's say we have another English sentence called Richard has at least 2 brothers. So now we define a function called brother x comma Richard, and now we have to use this to say that Richard has at least 2 brothers. So now we do that. We take another variable y and we say that brother x comma Richard is true and brother y comma Richard is true, and this is true for at least some x and some y. Okay, so there exists x and y for which x is a brother of Richard and y is also a brother of Richard. Now this may look alright at first glance, but if you look at it slightly more carefully, what you will realize is that this does not exactly say what is being conveyed by the sentence in English. And the reason is that here nowhere have we specified that x is not equal to y, because here I could take y to be the same as x and then this statement would be true, but that would not imply that Richard has at least 2 brothers. So we need to modify that and we need to add a and of not x equal to y. Okay, so this is true, this is true, and this is also true. If this is also true, what that means is that x is not equal to y. Okay, and this is how you ensure that brother x comma Richard and brother y comma Richard are true for a value of x which is different from a value of y, And this is what ensures that Richard has at least two brothers, and these two brothers are actually different from each other. Let's take another sentence where now instead of just leaving it as two brothers, I am specifying that these two brothers are John and Jeffrey. Okay. So now is it enough to just say that brother John comma Richard and brother Jeffrey comma Richard? The answer again is no. And there are two reasons for this. The first reason is that John could be same as Jeffrey. So we need to specify very clearly that John and Jeffrey are two different people. And the other thing that we need to clarify is that there is no other person who is a brother of Richard. Because this sentence clearly says that Richard has two brothers and they are John and Jeffrey. So the first thing we do is that we specify that John is not equal to Jeffrey. But again, remember that this not equal to is not a part of the first order logic, first order logic connectives. So you need to actually write it in this particular format, not John equal to Jeffrey. Okay. Then we also need to specify that, there is no third person. So what that means is that we do an AND with for all x, if brother x comma Richard is true, then that implies that x is either equal to John or x is equal to Jeffrey, and there is no third option. Okay, so this we have specified using this additional condition. Okay, so the point that is being made over here is that in first order logic, when you want to express certain ideas from English language, you have to be very careful about the assumptions. Okay, if you are not very careful, you may leave out certain very critical and crucial things which may convey a very different picture from what the English sentence actually is trying to convey. And here you need to be very, very careful. Okay, so now let's look at how do you deal with these operators, and how do you simplify things when you have more complex settings. So you have, let's say, this quantifier, which is the for all universal quantifier, and your statement is for all x not p is true, which means for all values of x p is false, and that is equivalent to not there exists p. Okay, so what does the left hand side say? Left hand side says for all x not p is true, which means for all x p must be false. Let's look at the right hand side. Let's forget this not operator for a while. If we just had there exists x such that p is true, which means there is at least one x for which p is true. If I put a not in front of that, that means that there is no value of x for which p is true. Okay, and that, as you can see, is exactly same as the left hand side statement. So now one simple way to remember this is that when you have, let's say, a not outside a there exists operator and you want to take it inside, you take it inside but just change the there exists to for all. Okay, similarly you have this statement not for all x p implies there exists x not p. Again, there is a not outside this for all symbol. You take the not inside and for all changes to there exists. So what does this mean? Again, forgetting this not symbol would mean for all x p is true. Not means that there could be some x for which p is not true. And this is exactly what the right hand side says, that there exists x for which not p is true, which means p is false. Okay. Again, to remember, if you have a not outside for all, just take it inside and change the for all to there exists. Similarly, you can have a statement like this where you have two negations. When you take the negation inside, this negation cancels out, and so you get p, and this there exists symbol we change to a for all symbol. Similarly, if you have not for all x not p, you take the not inside, not cancels, and for all changes to there exists. Okay, so this is something very very important that you need to remember and be and use it, whenever you see this not symbol outside a there exists or a for all quantifier. So the important thing about this first order logic is that this is sufficiently powerful for most practical applications. Okay, it was found that set theory can be formulated as an axiomatized system within the apparatus of first order logic. Okay, so you do not need to go to second order or higher order logic. People have found a way to axiomatize set theory within the apparatus of first order logic. Now the cost is several kinds of completeness theorems, but at least we are able to avoid what is called a Russell's paradox, which is an absolute killer. And this was done, under this Zermelo-Frankel set theory, and this is something which is very vital for, very very vital for mathematics, because most of mathematics is represented using set theory. Arithmetic, mereology, and a variety of other powerful logical theories could be formulated axiomatically without appeal to any more logical apparatus than first order quantification. So you do have second order, third order, and other higher order logic, but for most practical purposes, first order logic is more than sufficient. Okay, and this is why first order logic is so important, because it helps you in doing computation, deriving a lot of important theorems without getting into these dirty paradoxes like Russell's paradox. But here another crucial point that you must understand is that to arrive at this formulation of set theory and finding the right balance, that you are giving up some kinds of completeness but also avoiding what is called Russell's paradox, required lot of hard work by mathematicians and logicians. It was not that what is called logic was so obvious that people wrote down the answers on day one. It has taken centuries of hard work to arrive at what is called first order logic, and which satisfies our requirements from a practical perspective. So let's start looking at some more examples to see how first order logic could actually be utilized in solving various kinds of problems. So this Wumpus world problem we had seen earlier, and now so we had seen how to represent these rules and environment specifications using propositional logic. Now let's look at how we can represent the same thing using what is called first order logic. So let's say we know that we have a glitter in one of the cells, and in the cell where we have glitter, the best action is to grab the gold and to go back to start. So what do? You define a function called glitter of t, where t is the time. So at time t, if the agent experiences glitter, then the best action would be to grab that gold. Okay, so here I have to put for all t. Okay, so for all t, which means at any time t, if glitter of t is true, then the best action is to grab it. Similarly, I know that if I have a breeze in a particular cell, then one of the adjacent cells has a pit. Okay, so to describe this, I make two functions. One is called adjacent r comma s. So r is a cell and s is another cell. So if r and s are adjacent, then this function will output true. Okay, and you have a function called pit of r. If r has a pit, then pit of r will also be true. Okay, so how do I describe this? What I do is, first of all, is that I use a AND operator over here, which means that if r and s are adjacent and r is a pit, then this whole thing will be true. Okay, And what I can say is that for all S, okay, for all cells S, if breezy of S is true, then there will be at least one R which will be adjacent to S and which will also have a pit. Okay, this is what this sentence is conveying, and this is what we know from the rules of the game also, that if a particular cell is breezy, then at least for one of the adjacent cells, your cell will have a pit. Okay, so again, as you see, we have been able to represent the whole rule by a single statement in first order logic, unlike propositional logic where we had to write a separate sentence for each of the cells separately. We also know that if there is a wumpus in a particular cell, then the neighboring cells will have a stench. Okay, so I have a function called smelly of S, and if my S is smelly, then then the adjacent cell will be the home to wumpus. Okay, so here again I am using the adjacent function. So I have adjacent home of wumpus comma S. So for all S, if S is smelly, then I know that the cell which is the home to my wumpus will be adjacent to my cell S. So now again, as you can see, this rule again has been represented using a single sentence in first order logic. Now that we have seen the basics of first order logic, now we are going to see how to do inference in this system of logic. It will be very similar to how we did in the case of propositional logic. The only difference is that you have to be careful when you have the universal quantifier for all and the existential quantifier there exists. So a very simple way of doing inference in first order logic is to reduce your statements or whatever you want to infer to propositional logic. This is the most basic and the most simplest way of doing inference. Okay, so if you have any formula in first order logic, you can convert that to a list of propositions by substituting the variables with different kinds of objects. You may say that, okay, now how do we handle these variables when you have a infinitely nested term, something like this. Now that again has been shown by theoretician that this can be taken care of, although we are not going to get into the details. I have mentioned it just for your knowledge that that infinitely nested terms is not a limitation to this approach of reducing first order logic statements to propositional framework. And what is known and what has been shown is that every entailed statement in first order logic can be proven, which means that if you know that alpha entails beta, and if you know that alpha is true, then you can also prove that beta is also true. But for non-entailed statement, the algorithm can go into an infinite loop. And this is why the first order logic inference system is semi-decidable. That if your algorithm or if your statement is entailed by another statement which you know to be true, then there is a system by which you can prove that other statement. But for non-entailed statement, there is no way for you to either prove or disprove that statement in all cases. And that's why first order logic is semi-decidable, and this is one of the limitations of first order logic. But because it is so powerful and so useful in many other ways, and because higher order logical systems get into more complicated kind of paradoxes which are totally unacceptable, so we have to live with this reality and limitation of our theoretical frameworks. So now let's see how would you reduce a statement of first order logic to propositional logic. If you do not have these universal quantifiers and existential quantifier, then it is very straightforward, because then the statement is almost same as how it would be in propositional logic. The difference comes in when it has a universal or the existential quantifier. So what you do is that, if let's say your statement is, for all v, which is a variable, alpha is true, then you can substitute any object g in place of the variable v. And okay, then this is the syntax by which it is written. So SUBST stands for substitution, and inside the brackets you have in curly brackets v/g. What that means is that in place of v you are going to write g. So wherever v is occurring in this statement alpha, you just replace that by any object g, and the reason it works is that your statement which is true is, for all v, alpha is true. So this is fairly simple. Let's see a simple example that you let's say have, for all x, human of x, let's say, is true. You can take a substitution, theta is equal to x/John, and so if you write John inside this function human, then this will also be true. Okay, and this is true because human of x we know is true for all values of x in our domain. For existential instantiation or for existential quantifier, you cannot replace this v by any object in your system, because what this says is that there exists v for which alpha is true. Now, which is that object for which alpha is true, that is not known in this statement. So what you have to do is that you have to replace v by a symbol k, but the trick is that the symbol k should not appear elsewhere in your knowledge base. So k has to be different from any other object or anything else that exists in your current database, and that will differentiate it from everything else. And this is a major difference between universal instantiation and existential instantiation, that when you have for all, you can replace this v by any object, and since this statement is true for all v, this statement will also be true for g. But when you have there exists, you have to replace it by a new symbol which is different from anything else that exists, to avoid confusion. Okay, we are going to use this in an example later on which will make it clear. So how do you do inference? In propositional logic, you have something called modus ponens. What that means is that if alpha implies beta, and if alpha is true, then beta must also be true. Now there is a generalized version for first order logic. Before looking at that particular statement, we need to have one condition, which is that if I take a statement pi prime and if I make a substitution theta in it, if I take another statement pi and if I make the same substitution theta in it, then these two resulting expressions are the same for all I. Okay, so this is a assumption that is required for the generalized version to hold true. Okay, so I have this set of statements pi prime. I make a substitution of theta. I have another set of statements pi. I make the same substitution theta, and both of these are exactly the same for all values of I. Now the generalized version is the following, that if p1 prime, p2 prime and so on up to pn prime are known to be true, and we know that p1 and p2 and so on up to pn implies q, then we know that p1 prime and p1 are the same when we make this substitution, p2 prime and p2 are the same when we make the substitution, and we know that all these p1 prime, p2 prime and so on are true. Then we can take q and make the same substitution theta, and that statement will also be true. Okay, so this is the generalized version of the inference system for propositional logic. Okay, so let's see an example. Let's say P1 prime is king of John, P1 is king of some variable x, P2 prime is greedy of y, and P2 is, let's say, greedy of some variable x, and the substitution is the following, that theta is a substitution where you replace x by John and you also replace y by John, and this q is evil of x. Okay, so what does this P1 and P2 implies q means? That if x is a king and if x is greedy, then x must be evil. Okay, so now what can we infer from this generalized version is that because my substitution x slash John makes P1 prime and P1 equivalent, my substitution y slash John makes P2 prime and P2 equivalent, and I know that P1 prime and P2 prime are true, then I can make the substitution x slash John in evil of x, and this statement will also be true. Okay, so this is how we are able to infer evil of John, means John is evil, by using this generalized version. Okay, so this is a leading factor in what is called forward chaining, that you take some sentence, you infer something from there, then you take that resulting statement, you infer something further from there, and you keep on moving forward till you arrive at your particular solution, and that is what is called forward chaining. So to summarize, you start with expressions in the knowledge base, you apply the rules of inference in the forward direction, you add new expressions until no further inferences can be made. Okay, so what does this mean? You have a knowledge base which have certain sentences which are known to be true. You apply the rules, which some of which we have seen and some others which we are going to see. You apply the rules in the forward direction and you keep combining these existing statements to find new statements. At some point you will not be able to find a new statement, and at that point you kind of stop and your forward chaining process is complete. Okay, in order to carry out this forward chaining process, generally the clauses or the sentences in first order logic are represented using what is called the horn clause format or the definitive clause format. But the thing is that not every statement can be represented in this form, but still these are very, very useful. So what are these two formats? The horn clause has at most one positive literal, meaning out of all the literals or the atomic sentences in the statement, everyone should have a negation except for at most one can be positive. So either all of them are negative or at least one is positive. A definite clause has exactly one positive literal and everything else is negative. So formulating your first order logic statement in this form has certain advantages and makes things simpler, but as the last statement says is that not every knowledge based statement can be converted into that format. So let's take an example and see how you would use forward chaining to arrive at the inference that we are interested in. So what is given to you is this statement or this situation. It says, the law says that it is a crime for an American to sell weapons to hostile nations. The country Nono, which is an enemy of America, it has some missiles, and all of its missiles were sold to it by Colonel West, who is an American. And your task is to prove that Colonel West is a criminal. Okay, so this is like a law proceeding that is happening, and you are, let's say, a lawyer, and your task is to prove that Colonel West is a criminal given this information which is available to you in English language. So now this information has to be converted into the language of first order logic. So what essentially we have from our summary of the situation is that if X is an American, if Y is a weapon, if X has sold Y to Z, if Z is hostile, then if all of these four conditions are met, then one can infer that X must be a criminal. Okay, this is what the first line says. The law says that it is a crime for the American of X to sell weapons, weapon of Y, then sells to hostile nations, hostile of Z, and you have it is a crime means that X is a criminal. Now using the second sentence and this law, we need to infer that Colonel West was a criminal. So let's see what we have got. What we have been described is that Nono is an enemy of America, which means I can take a function enemy and with two arguments, Nono comma America, and this will be true. Now remember that in what is the law says that Z must be hostile, but what is given to us is the word enemy, and it is not obvious that these two are the same. So we have to make a conjecture that if Z is an enemy of America, if this is true, then I can infer that Z must also be hostile. Okay, so now because I have enemy Nono comma America is true, and now I'm making this assumption, I can infer that Nono is a hostile country. So the first condition of this statement has now been found to be true. Let's see what we have got. We know that Nono owns a missile. It says the country Nono, an enemy of America, has some missiles. So there exists Y, for which Y is a missile and for which Y is owned by Nono. Okay, so this also has been verified. So now here we can see how to use the generalized version of the inference rule that we just saw, is that you can replace this Y by some symbol M1, which is not a part of your knowledge base. So M1 is a missile and M1 is owned by Nono. So now we also need to now specify that a missile is a weapon, because in the law, which is the first sentence, nowhere has that been mentioned, and neither in the second sentence also. So this is another assumption that we are making, that if Y is a missile, then Y must always also be a weapon. Then we also know that West is an American, which is very simple, which is given to us that Colonel West is a American. Okay, so what do we have now? We have hostile of Z, which means this has been satisfied. We have weapon over here, so weapon is also has been satisfied. American of X, American of West has also been specified, and so what is remaining is this function sells, and that we know from here is that Nono has some missiles and all of its missiles were sold to it by Colonel West. So if Y is a missile and if Y is owned by Nono, then that missile must have been sold to it by Colonel West. So now all the four ingredients of our law are available to us, and when all these four are true, then one can infer that this X or this Colonel West must be a criminal. So by using this procedure, we have been able to arrive at our conclusion. But again, re-emphasizing this point that to arrive at the conclusion, it was not just sufficient to express the English sentence in terms of first order logic, but you also had to make certain assumptions to connect the concepts in the second sentence to the concepts in the first sentence, and that is a more tricky and difficult part that can come only with practice and experience. So this is a pictorial representation of the process of forward chaining. So we began with the statements that West is an American, M1 is a missile, M1 is owned by Nono, and Nono is an enemy of America. From enemy of America, we inferred that Nono must also be hostile. From missile of M1, we inferred that M1 must be a weapon. From M1 being a missile and M1 being Nono, we could infer that it must have been sold by West. And now because all four of these conditions are true, we can infer that West must have been a criminal. And this is the process of forward chaining. Similarly, we have a related process called backward chaining, where instead of starting from the atomic sentences, we start from our desired conclusion, and we see then working backwards is that whatever is required for that conclusion to hold true is that supported by the available information. Now I know that from my law that if West is a criminal, then West must be an American. West must have sold some weapon Y to this country Z, and that country Z must be hostile. Okay, now again going backwards, how do we know that Y is a weapon? Because we know that Y is a missile. So that's an assumption that we are making. How do we know that West has sold missile M1 to country Z? That is again given to us that the country Z owns some missiles M1, and whatever missiles it owns, they have been sold to it by West. So this is also satisfied, and we know that Nono is hostile because it is an enemy of America. So this is the backward chaining process, that you keep going backwards and see if the ingredients which are required to prove that statement, whether all those ingredients are true or not. In this case, they have been turned out to be true, and that is the process of backward chaining. There is a related process called resolution and refutation, which is also extremely important and extremely powerful. So let's see what does this method contain. So resolution is a theorem proving technique that proceeds by building refutation proofs, meaning proofs by contradiction. So if you have to prove a particular statement to be true, you assume the opposite statement to be true and see if that leads to a contradiction. Okay, we will see again some examples which will make it clear to you. So resolution is a single inference rule, and that can efficiently operate on what is called a conjunctive normal form. So we are going to look at some examples of what this conjunctive normal form is, and that will again make it very clear, and this is a very, very simple procedure to follow. So a conjunctive normal form, or what is called CNF, is a sentence which is represented as a conjunction of clauses. Okay, so CNF statements consist of a number of conjoined clauses. So what are conjoined clauses? These are clauses which are joined by the logical AND operator. Okay, and each of those clauses which have been conjoined, they can consist of either a single term or multiple disjoined terms, which means which are terms joined by OR. Okay, so this is a very, very important thing to remember, that when you have something in a conjunctive normal form, you cannot use implies and all those other equivalents and all those other connectives. You have to break everything down in the form of and, or, and negation is allowed. And there's a very specific form that you should have different clauses. Each of those clauses can be a single term, or it can be something consisting of or, and these clauses must be joined together by the logical AND operator. And the terms which are individual propositional variables, they may or may not be negated. So the NOT operator is allowed for individual propositional variables, not for a composite thing. And the other things like implies and equivalence, they are strictly not allowed. Okay. And what is known is that every sentence of first order logic can be converted into an inferentially equivalent CNF sentence. We will see how to do that. Okay. So this is, let's say, a simple example of a statement in CNF form. Why is that so? So we have these clauses. So we have 4 clauses which have been connected by the logical AND operator, and these are all individual atomic sentences with a not operator. And you have a composite clause, but that only has the or operator, and it does not have and, it does not have implies, it does not have equivalence. So that is why this particular sentence is in the form of a CNF. So like every proof of contradiction, what you do is that you begin by assuming the opposite of what you wish to prove, and then show that this fact would lead to a contradiction. So if you want to prove that the sun rises in the east, you start with the statement that sun rises in the west, and you show how that leads to a contradiction. And since that happens, you know that the opposite of that must be true, and which is that sun rises in the east. Okay, so this is how resolution and refutation work. So before getting into the process of the inference, let us look at how do you actually convert a given sentence in first order logic to something that is in the conjunctive normal form, because whatever inference system we are going to apply under this resolution and refutation method, that we are going to do using the CNF format. So the first thing that you do here, you have a equivalence. So you need to eliminate this equivalence and replace this equivalence by alpha implies beta and beta implies alpha, because that is what equivalence means, that it is a bidirectional relationship. So here I have B11 is logically equivalent to P12 or P21. So again, remember the Wumpus world problem. Here what that means is that if you have a breeze in 1,1, that would imply that there is a pit in 1,2 or there is a pit in 2,1, and reverse is also implied. That's why you have the symbol of logical equivalence. So when you replace this equivalence with 2 implies, you get B11 implies this and this implies B11. The next step is to eliminate the implies with this format, not alpha or beta. So if you look at the truth table for alpha implies beta, and if you look at the truth table for not alpha or beta, you will see that they are exactly the same. Okay, I will not spend time in how that is the case, because that is something that you can check very easily. So please do this, write a truth table for alpha implies beta, write a truth table for not alpha or beta, and see whether they are same or not. You will find that they are the same. Okay, so here in our sentence we have 2 implies operators, so we will convert that to not alpha or beta. So here when this implies goes away, there will be a not which will come in front of B11, and there will be a or symbol which will come over here. Similarly, a not symbol will come in front of this thing, and it will be or B11. Now we need to take the not inside, because CNF requires the logical not to appear only in literals. So you cannot have a not outside this composite statement. So you need to move the not inwards. So when you do that, the or operator becomes a and operator. Okay, so you have not P12 and not P21. The last thing is that you need to open up this thing, because in CNF your AND operator cannot appear in a composite clause. A composite clause can have only or operators, and these composite clauses must be conjoined together using the logical not operator. So now finally when we open this up, we get this term. This term is fine because it only has or and a not in front of atomic sentence, and this one becomes not P12 or B11, and this AND operator comes over here, and then not P21 or B11. So this is a representation of my original statement in the CNF format. Now let's see how we can do inference by using this particular format. So let's say I have this statement which let's say I know to be true, that so this first part is coming from my environment rules or rules of the game, and this second part is let's say coming from my actual sensory input. So I am an agent who is playing the game, and I do not experience a breeze in cell 1,1. That's why not B1,1 is true. And using this, I need to infer that not P12 must be true, which means that P12 must be false, which means that there is no pit in cell 1,2. So for us, from a common sense perspective, that is pretty obvious, but proving that from a logical perspective is not very easy, and that we need to see what is the process that we need to apply. So the first thing is that we need to write this in the form of a CNF. Now the left hand side we have already written in the CNF form, and we just need to add a AND not B11, and now this whole thing is again in CNF form. Okay, so now what we do is that we take this part and then see what to make out of it. So what we have done is that we have taken this whole thing, put it inside brackets, and then we will work with this. So now we can take this B11 inside, and what that will give me is not P21 and not B11. This OR operator will come over here, OR, and B11 and not B11. So what is this? B11 and not B11. This is obviously always false. Okay, because this can never be true, because if this is true then this is false, if this is false then this is true, and an AND operator will obviously give us false. So when you have a clause which is OR with a false, then the false one just goes away, and what remains is just that statement itself. Okay, so now what I have is this whole thing and not of P21 and not of B11. So comparing with the original one, just this B11 is now gone, and these two are as it is remaining. Now what we can do is that we can look at this not B11 and combine it with this not P12 or B11 in a similar fashion and see what we get. When we do that, I am not going to do the whole process, and you can check for yourself that when you do that you get not P12 and this not B11 remains. Okay, same thing, you just do not P12 and not B11, then this OR symbol, and then B11 and with not B11. Again you will get a false which will go away, and what it will leave you with is this. So now you see we have what we wanted to prove. This whole statement is true, which means each of its constituents must be true, which means not of P12 is true. So this is how we are using CNF. So this is not exactly resolution and refutation because we have not exactly done a contradiction over here that we will see later on, but this was just to show you how you can use the CNF form to do inference in the first order logic framework. So going back to the another problem that we saw just now, that when you have for all x American of x and weapon of Y and cells and hostile implies criminal. To convert that into the CNF form, you can drop for all because that doesn't really matter, and you remove this implies, it will become not of this whole thing or this thing, and then you take the not inside, you get this thing. So you have a single clause over here. You do not have a and operator. Everything is just connected by or. So it is a single clause that is there in your CNF format. Let's see another sentence and see how to represent that using CNF, because sometimes it can be a bit complicated. So the sentence we have is, everyone who loves all animals is loved by someone. What does it mean? That if you love all animals, then there will be at least one person who will love you in return. Okay, it may not be a person, it will be some entity, but yeah, if you love all animals, then there will be some entity who will love you in return. So how do we represent that using first order logic, and especially in the CNF format? So now you have this statement, you have for all x and you have for all y. Animal of y implies loves x comma y. So what does this mean? That for all x, if y being an animal implies that x loves y, then we can say that there must exist a z for which loves z comma x is true. Okay, so for all x, if that x loves all animals, then there will definitely be a z which will love x. Okay, so now how do we convert this into CNF? So first thing is that you need to eliminate the implications. So to eliminate that, we replace this implication by not alpha or beta. Okay, again, as I said, please do check this. Write a truth table for alpha implies beta, write a truth table for not alpha or beta, and make sure that these are one and the same. So now when you do that, you remove this implies first, so you get a not animal of y or loves x comma y. Okay, now next you remove the next implication, so you get a not which is outside over here and a or over here. Then after that, you need to move the not operators inside. When you do that, your not comes inside over here and rest everything is the same. So how do you deal with this not? You take it further inside, and this for all will convert to there exists, and this clause will convert to this not will cancel. You will get animal of y, the or will convert to a and you will also have a not in front of loves. Okay, now you need to do scholemization. What is scholemization? That is removing the there exists symbol. Okay, so now if you apply scholemization in a naive way, what you will do is that wherever you have y, you will replace that by some object a, and wherever you have z, you will replace that by some object b. But this is actually wrong, because what it says is that for all x, if this statement is true where a is some animal, then this part is loves b comma x. But the thing is that you may actually have a different z for each x. What the z represents for each x is different, so you cannot exactly replace z by the same object b for all values of x. Okay, so this is wrong. So what you need to do is that instead of replacing that by an object, you need to replace that by another function. So instead of saying b, you need to say g of x, because the object can be different for each object x. Okay, so now these are called Skolem functions. So what is loved or what loves x is different for each x. Okay, and now finally we need to drop the universal quantifiers because they are not really required. So you finally have animal f of x and not of loves x comma f of x or loves g of x comma x. Now this is not exactly in the CNF format because I have two clauses which are connected by a or, and I have a and inside one of my clauses. It should be the other way around. I should have clauses with or inside which should be connected by using the and operator. So that is what you need to do. You need to distribute the or over the and. When you do that, you get this animal f of x or loves and this statement, the not of loves and the or of loves. So now this is something that is not very easy to interpret, so I'm not going to explain what exactly this means, but take it, something that is a result of your inference procedure. So here there is a small typo. There should be a bracket after this f of x also. Okay, so just remember that when you write it in your notes more properly. So let's use this CNF format to actually do inference using the procedure of resolution and refutation. So let's say you have some facts which are given to you, which is that if you go swimming, you will get wet. And let's say you also know that if it is raining and you are outside, then you will get wet. If it is warm and there is no rain, then it is a pleasant day. Okay, and it is known that you are not wet, it is known that you are outside, and it is known that it is a warm day. So what you need to now figure out is certain statements, but before looking into those statements, let's represent this information in the form of first order logic and especially in the CNF format. So you will have the first sentence which says, if you go swimming, you will get wet. So swimming implies wet, but implies is not allowed in the CNF format. So we will do not swimming or wet. We have again converted this using the rule that alpha implies beta has to be converted to not alpha or beta. The second statement says if it is raining and if you are outside, then you will get wet. So it means if it is raining and you are outside, then it implies that you are wet. Again, representing this using the CNF format, you will have a not outside this whole thing or wet, and then when you take the not inside, the and will convert to a or, and you will have a not operator besides rain and outside. Okay, so again, if this is not very clear, just take a pen and paper, write it down, and then it will make perfect sense. The third sentence is if it is warm and there is no rain, then it is a pleasant day. Okay, so if it is warm and there is no rain, that implies it is pleasant. Again, using the same rule, we get not of warm or rain or pleasant. Fourth statement says you are not wet, which is just not wet. So there is nothing much to do over here. The fifth one says you are outside. There is again nothing much to do over here. The sixth one says it's a warm day. Again, very, very simple. So it's a warm day. So now what we have done is that we have represented the statements that were given to us in English language and converted them to statements in first order logic, and then we have written those statements in the CNF format. Okay, so these are the rules, or these are the facts which are known to us, and what you need to prove is that you are not swimming. So how do we do that? In resolution and refutation, we assume the opposite to be true, and see if that leads to some kind of a contradiction. So how do we do that? We take this assumption and we take a relevant statement from the CNF format and see what do we get from there. So if we take swimming and if we take not swimming or wet, then by combining these two, we can infer that wet must be true. Okay. So if I am swimming, which means swimming is true, which means that not swimming is false. But if this whole thing is true, then, and if this thing is false, then wet must be true. So I get wet if I consider these two statements. However, if I look at my fourth statement which says not wet, so if I take not wet, and when I say that on one hand my conclusion is that I am wet, on the other hand my conclusion is that I am not wet, when I combine all of that, I get a contradiction, and so I know that my initial assumption of swimming must be wrong, which means that not swimming must be right. Okay. So here, by using this process of resolution and refutation, I have been able to arrive at a contradiction, which means that my initial assumption was wrong, which means that the reverse of that must be true. Okay. So again, how did I do that, and how does the CNF format help? The CNF format helps because when I write it in this particular way, all of the individual clauses must be true for my whole thing to be true. If out of these 6 statements, even if one is false, then the composite thing will be false, which is very easy to infer because all of them have been combined using the AND operator. Okay, and this is why the CNF format is so powerful. There is another example which I am not going to solve for you, but I will leave it to you as a exercise. Is that if you are given these statements, that given these following statements, all of which are assumed to be true. So what is the statement? If you are lactose intolerant, then you cannot eat ice cream. Okay. The second one, if you are lactose intolerant, then you cannot eat cheese. If you are lactose intolerant, then you cannot drink milk. And then fourth one is that you eat ice cream. Okay. So the exercise is that you need to convert these statements to propositional expressions, and then convert these expressions into single CNF form, and then prove using resolution that you are not lactose intolerant. This must be true. Okay. So I'm leaving this as an exercise. If you do it, that will be a very good practice for you. So this is all about first order logic, and if you have any questions, please do feel free to reach out to me. Thank you.